Continuing on Physical Chemistry, Chapter 4, we're beginning Section 6 now. We're going to calculate changes in state functions. First, let's do a calculation of the change of entropy. Let's say we're going from state with pressure 1, temperature 1 to another state with pressure 2 and temperature 2. Now remember, entropy is a function of temperature and pressure. So we write the differential of entropy as the partial derivative of S with respect to temperature holding pressure constant times the differential of temperature plus the partial derivative of entropy with respect to pressure holding temperature constant times the differential of pressure. Now we're going to use the Maxwell relations and the definition alpha to substitute. So we're going to have differential of entropy is equal to the heat capacity at constant pressure divided by temperature times the differential of temperature minus alpha times volume times the differential of pressure. Now we're going to find the integral of that. So we're going to get delta S is going to be entropy of state 2 minus entropy of state 1, of course, which would be the integral from state 1 to state 2 of the heat capacity at constant pressure divided by temperature with respect to temperature, minus the integral from state 1 to state 2 of alpha times volume times the differential of pressure. Now these are line integrals, so we have to integrate them separately. So the heat capacity, we're going to, at constant pressure, we're going to say is a function of temperature and pressure. So this is measured under constant pressure, obviously, but we can use in any process. So we're going to say alpha is a function of temperature and pressure, and volume is a function of temperature and pressure. So let's say we have a two-step path. We're going to have constant pressure, then constant temperature. So here's pressure, here's temperature. So we have the pressure at state 1, the pressure at state 2, the temperature at state 1, the temperature at state 2. So we're going to have segment A, which is isobaric, and then step B, which is isothermal. So the change in entropy for A is the integral from temperature 1 to temperature 2 of the heat capacity at constant pressure with respect to temperature, or divided by temperature with respect to temperature. The heat capacity at constant pressure is a function of temperature. So that means when you integrate that, you'll have to remember that. And then the change in entropy for segment B is the integral from pressure 1 to pressure 2 of alpha times volume times the differential of pressure. Now if you have a perfect gas, you could say alpha is just 1 over temperature. And if you have a perfect gas, you could say volume is equal to nRT over P. So because entropy is extensive, the change in entropy is going to be the change in entropy for step A plus the change in entropy for step B. We can have delta change in entropy for phase transitions, if any. So we already did something like this before. We'll do it again because it's important. So if you have an irreversible process, what you can do is find a reversible path, do the calculations on that, and then since entropy is a state function, the results had better be the same. So we used the example before of how you're going liquid water at minus 5 degrees Celsius in 1 atmosphere, it'll automatically, spontaneously go to H2O liquid. Oops. Oh, did I screw this up? I think I actually screwed up the thing here. Okay, so this is the reverse of the example before. We're going to start out with solid water if somehow it's positive 5 degrees, and then it's going to irreversibly melt to a liquid at 5 degrees. This is the reverse of what we did before, where we had liquid water at minus 5 degrees and it spontaneously froze. But it's the same thing. So you just divide it up into segments. We could say, okay, the solid water, we can reversibly cool it down to 0 degrees, and then we can reversibly melt it, and then we can reversibly heat it up to 5 degrees. So we can do the entropy of segment 1, the entropy of segment 2, the entropy of segment 3, add them up, and since entropy is a state function, it'd be the same as whatever happened irreversibly. So the change in entropy for state 1 is just the integral from temperature 1 temperature 2 of the heat capacity divided by the temperature with respect to temperature. Remember, T has to be absolute, like in kelvins. It can't be degrees. And in this case, since we started out with solid water, so it'd be the heat capacity of the solid ice. And then the heat capacity, remember, is the differential of the heat at constant pressure divided by temperature. Now, the heat capacity is undefined for phase transitions, though. So, for delta S for segment 2, which was the melting of the ice, then we had the change in enthalpy of the fusion divided by the change in temperature. So this is the heat of fusion. It's enthalpy. It's really the same thing. It's a type of energy. And then for the third segment, when the water is being heated back up to 5 degrees Celsius, we have the integral from temperature 1 to 2 of CPE, the heat capacity constant pressure for liquid water, divided by temperature with respect to temperature. Now, what about calculation of the change in enthalpy and the change in internal energy? Again, going from some state with pressure 1 and temperature 1 to a different state with pressure 2 and temperature 2. Well, we can say enthalpy is a function of temperature and pressure. So the differential of enthalpy is the partial derivative of enthalpy with respect to temperature holding pressure constant times the differential of temperature plus the partial derivative of enthalpy with respect to pressure holding temperature constant times the differential of pressure. Now the heat capacity at constant pressure is also equal to the partial derivative of enthalpy with respect to temperature holding pressure constant. So we're going to just get the change in enthalpy is the integral from state 1 to state 2 of the heat capacity at constant pressure with respect to temperature plus the integral from state 1 to state 2 of volume minus temperature times alpha times volume with respect to pressure. And that's assuming no phase transition. The change in enthalpy, remember, if we divide it into steps A and B or whatever, since enthalpy is extensive, we can just add up the enthalpy for step A and the enthalpy for step B, etc. So if there is a phase transition, then you do the enthalpy for step A, enthalpy for step B, enthalpy for phase transition, etc. So there are two calculations you can use to two options you can use to calculate the change in internal energy. One, so say that the change in internal energy is just the change in enthalpy minus the change in pressure volume. So we can use this if we were able to figure out the appropriate stuff. Otherwise, now remember, a volume change can result in a pressure change. So internal energy is a function of temperature and volume, or it can be written as a function of temperature and pressure. So just like we did above with the change in enthalpy, we have the differential of internal energy is the partial derivative of internal energy with respect to temperature holding volume constant times the differential of temperature plus the partial derivative of internal energy with respect to volume holding temperature constant times the differential of volume. Now we can just do the substitutions for that, and we can integrate to find our change in U. Our finite change in U. This is our infinitesimal change in U. So what about calculating the change in Gibbs free energy, or the change in the Helmholtz free energy? Well, if it's isothermal, then we could just say the change in Gibbs free energy is equal to the change in enthalpy minus temperature times the change in entropy. That's assuming constant temperature, though, obviously. So we can find the change in enthalpy and the change in entropy just like we did before. Or we can take the differential of Gibbs free energy is equal to volume times the differential of pressure minus entropy times the differential of pressure. We're going to say it's isothermal, so the differential, that should be temperature. Holy cow, I screwed up here. dt. That's dt. So we're going to say it's isothermal, so dt is equal to 0. So this whole term is equal to 0. So the differential of Gibbs free energy is equal to volume times the differential of pressure. So we have the partial derivative of the Gibbs free energy with respect to pressure holding temperature constant is equal to volume. So integrating that, we just get the integral of the differential of Gibbs free energy is equal to the integral from pressure 1 to pressure 2 of volume times the differential of pressure. So we get the finite change in Gibbs free energy is equal to the definite integral from pressure 1 to pressure 2 of volume with respect to pressure, Or we could say, but remember, volume is a function of pressure. So to make sure we know that, we should write it as a definite integral from pressure 1 to pressure 2 of volume as a function of pressure with respect to pressure. So what we need to do then, we need a function of volume for volume as a function of pressure. For example, with the ideal gas, solve for volume, we've got it as a function of pressure. It'd be just nRT over pressure. So for an ideal gas, or perfect gas, we could just say, okay, the change in the Gibbs free energy is equal to the integral from pressure 1 to pressure 2 of nRT over P dP for the perfect gas. Now, there is a special case at equilibrium. The change in entropy is equal to Q reversible over T. So T delta S is equal to Q reversible. If P is constant, then delta H is equal to Q. So if we have temperature and pressure both constant, then delta G is equal to delta H minus T delta S. But this is only for a reversible process and constant T, because we pulled that out. So delta G is going to be equal to Q minus T times Q over T. The T's cancel out, the Q's cancel out, you end up with delta G is equal to 0. So when you're at equilibrium, delta G is equal to 0. So when you, here's our Gibbs free energy versus the reaction coordinate. We showed before how if you're on either side of equilibrium, you're going to be changing towards dg is less than 0. So eventually when you get to the bottom here, at the bottom of any function, the derivative is always equal to 0. So dg is equal to 0 at equilibrium. Now the Helmholtz free energy, delta A, is equal to delta U minus T delta S. So that's going to be equal to Q plus W minus T delta S, which is going to be equal to Q plus W minus T times Q over W. These cancel out, these cancel out. So the change in the Helmholtz free energy is going to just be equal to the work. The delta A is going to be equal to work, assuming the only work is pressure volume work, of course. So delta A is going to be equal to the integral from V1 to V2 of minus times the pressure with respect to volume. So we also have the differential of Helmholtz free energy is equal to minus the entropy times the differential of temperature minus pressure times the differential of volume. So if we say we're at constant T, this term disappears, then we end up with the differential of Helmholtz free energy is just equal to minus pressure times the differential of volume. Integrating that, we get the change in A, the finite change in Helmholtz free energy, is equal to the definite integral from volume 1 to volume 2 of minus pressure times the differential of volume. The problem is, though, both the change in Helmholtz free energy and the change in the Gibbs free energy are undefined if the temperature changes. So the Gibbs equations, these all apply only to a closed system, pressure volume work, a reversible process. And that's it for section 6.